So in this video we're going to look at graphing rates of change, and we're going to make a graph of a distance. We're going to make a distance time graph, and on our distance time graph we're going to read off average velocity. So we're going to look at the concept of average velocity. So let's start by imagining a little robot who travels along, well, starts from rest, travels along, and then comes to rest again, so decelerates and comes to a stop. So if we draw two axes, then our vertical axis is going to represent distance. So distance in meters, and our horizontal axis is going to measure time in seconds. And if we number these off, we'll have 1, 2, 3, 4, 5 then, 6, 7, 8, 9, 10. So we'll go up to 10, and then we've got a little bit more in case we need it. We'll number the horizontal axis up to 5 seconds initially, then for a further 2 seconds, so up to 7 here, and then for a further 5 seconds, which should mean we end up at t equals 12. Okay, now let's draw some interval lines then at first t equals 5, then t equals 7, and t equals 12. Excuse me. So what I'm going to do now is draw a line up to t equals, not t, but the distance of 3. So we've got 3 meters. In fact, if I number this, perhaps it's a bit neater. So we've got 3 meters here. So I'm going to stop accelerating at this point here at t equals 5. And I'm going to draw a curve because we're starting at rest. So if I draw a curve like this, there we go, and stop here, then what I've drawn is a curve that starts with a gradient of 0, but the gradient increases and increases until we get a constant velocity at this point here. So at this point here I'm going to pick up the curve and turn it into a straight line and draw it up to about here, so like that. And then finally we want him decelerating, so I'm going to have about 3 seconds and then tail it off until the gradient is 0 again. Like that. Okay, so we've got a curve, a straight line, and then a curve going in this direction. These two curves are both parabolas because we're accelerating our little robot constantly, and this is also a parabola, like a reverse parabola, because we're again decelerating constantly. Okay, now what I want to do now is calculate the velocity at any point on this curve. So if I was to use the straight line as an example, that would be very easy. It's just the rise over the run. It rises by 5.5 minus 3. So let's just number this axis actually, so that we've, there we go, finish off the numbering. So here we've gone up, we've risen by 2.5, and we've gone along by 2. But let's just start at this curve here, which is a curve, not a line, so the gradient varies at every stage that we move along it. We can take little snapshots. Okay, let's just, first of all though, let's just draw a line at the start where the gradient is 0. So let's start with that. So you can see the green line represents the gradient. The gradient is the angle of the slope, and the angle is exactly the same as the angle of the horizontal axis. So there's 0 rise, so it's 0 over whatever distance you like to take. So it's a zero gradient. If we take a snapshot here at t equals 1, then we'd have to draw a tangent to the curve like this. And you can see as the angle increases, then the velocity is increasing. In fact, it's increasing from 0. We've now got a velocity of, well, roughly 5 over 1. So 1 over 5, so 1/5 of a meter per second. Now, if I increase if I go to t equals 2 and draw a gradient here, I'd have to draw a tangent at this point here. You can see again the velocity, the steepness of the slope has increased, so the velocity has increased. And again, at t equals 3, I'd have to draw a steeper angle like this. T equals 4, steeper still, until finally I get to this point here at t equals 5, where the velocity is going to be continued in the second stage, in the period where he goes from t equals 5 to t equals 7. He goes along at a constant speed. Okay, so that's the general concept of increasing velocity. Let's just remove those lines now. Okay. And think of the concept of average velocity. Okay, so average velocity is when we don't measure at every point of the line, which we can't. It's varying all the time, so we wouldn't get a single figure. We just get a string of figures or a variable expression. But if we take average velocity, then we're going to draw a line so that we have just one speed over this distance of 3 meters. So if I draw my line from the start of this journey, from t equals 0 to t equals 5, then I'm going to be joining up these 2 points here. Okay, so now I'm ready to measure my average velocity for this part of the journey. So let's call this A. So at A, our average velocity is going to be the rise over run of this straight line. So it's 3 meters. So 3 meters. In fact, let's just label this velocity and just call it, well, we need to say it isn't the velocity, because as we've seen, the velocity changes all the way along here, and it's never the same, except right at the end. No, even at the end, it's never the same then, except here, I guess, where the tangent is the same as here. But most of the time, except at one instant, it is not the same as the average velocity. So what we've got to do always is notate it as average velocity. I'm going to put average velocity abbreviated like that. So the average velocity over the period A is 3 meters. So let's write 3. That's how much this point has risen over the run. So the run means how far has it gone horizontally. So 1, 2, 3, 4, 5. So it's 3 over 5 meters per second. And in other words, what we've got is a 3 to 5 ratio. So if I divide my 3 by 5, then how am I going to do that? Well, if I think of it as 6 divided by 10, okay, so if I double it, that might be an interesting way of doing it. So if I double it to 10, then I've got easier figures to work from. And 6 divided by 10, of course, is 0.6 meters per second. So my average velocity over this period, represented by the red line, is 0.6 meters per second. Okay, let's move to the second stage of the journey. Now remember, the gradient at this point is going to be different to the gradient at in the first period of the movement of this robot. So in the second period, we've got a steeper incline. So if I draw now this stage of the journey, okay, going along that gradient, then I can record the average velocity again. This time, again, as rise over run, so 2.5, so 2.5 over the run, which is 2 meters per second. And again, I want to simplify this. If I have if I don't have a whole number either in the numerator or the denominator, I'm going to just cancel that, double it again, and that will get rid of this decimal here, so I get 5 over 4. 5 divided by 4 then, which is 1. So 1, 5 into 4, 1 and 1 remainder, so 1 and 1/4, or 1.25 meters per second. Okay, and now let's draw the final stage of the journey. So this time we're going to go along here and finally to rest at t equals 12. But again, the speed or the velocity will change continually as we go along this line. So what I'm going to do is find the average velocity, so I've just got one value, which is going to be a kind of average of that line. It's going to be where the velocity was at one stage here, the gradient would have been about here, but it's going to be constant along our average velocity line like this. Okay, so now let's calculate this. So here we've got, now this isn't so easy to measure. I think what we've got here is half and 2, so it's 2.5 plus another half, so that's 3 and 1/4. Let's say then that the average velocity at this stage seems to be 3.25 over this time 5 seconds meters per second. And again, what I want to do is simplify this fraction. So how am I going to do that? I can double it, so I can get 10 in the denominator. That will give me 6.5 in the numerator. And in fact, that's quite a good thing to do, even though we haven't got a simplified fraction, fully simplified fraction, because 6.5 again divided by 2 gives me 0.65 meters per second. Right, let's just tidy this up a little bit so we can see our red average velocity lines here. And what I'm going to do finally is just check that I have got correct values here. I've got 0.6 I'm pretty confident about. Stage B, 1.25, well that was read off assuming this was half. I'm fairly confident of that, but I'm going to check. And this one here I'm much less confident of because I didn't have whole numbers here at all. So I'm just going to check stage 3 using a geometric method. Okay, now before we do that, let's just clear up a little bit more. So let's just erase these. And we're going to extend as well our horizontal time axis. And that's because I want to show a little bit more of the journey of this robot. So if I leave him at 0 velocity here, then I can leave him for 5 seconds. Then let's think about that. So 12 plus 5, that's going to be here. So t equals 17. And then we'll bring him home in 10 seconds. So that's going to be 10, so here, and that's then t equals 27. So just extending this graph to give us just a little bit more to work with. Let's draw our interval lines here, and then, well, if he's got 0 velocity, then I'm going to be drawing, time continues, so I'm going to be drawing along for 5 seconds, but I'm not going to be rising at all, so it's going to be a straight line. In other words, whenever you see a straight line on a distance time graph, then you know that means 0 velocity. Okay, now what we're going to do is, let's draw the other interval line here. We're going to bring him back home, and again just draw the average velocity, so from the start to the finish here, we're going to draw a red line, straight line representing his average velocity as he makes his way home. Okay, so let's call this stage D and stage E then. Now, a geometric check can be done using the idea of a triangle. In other words, the gradient, or the line here, represents the hypotenuse of a right-angled triangle. The rise is one side of the right-angled triangle, the run is the other. So all I need to do here is draw a line across from 3 meters along to here to complete my right-angled triangle, and measure the rise. Well, that was 3 over the run, which is 5, and so I'm confident that my answer for that was correct. 3 divided by 5 gives us 0.6 meters per second. And let's give it the alternative notation, because you often will see it like this, to the -1, but it doesn't mean that, it means meters per second. Okay, 0.6 meters per second then for stage A. Now stage B, what I can do is just extend this line until it does go through the corner of one of these squares, and so it hits a whole number in our coordinate numbering system. So if I extend from here up to, well, let's see where we get to. There we go, and we can stop there. And then just join this up. So if I draw up here, so rise up to 8, and draw along to t equals 9, then I can now calculate my velocity for stage B. Okay, so just measuring geometrically, I've got 5. Let's write it here. 5 is the rise over the run of 4, and that is what we calculated, which is 1 1/4, or 1.25 meters per second. So that's stage B. Now stage C is perhaps the trickiest one here, because none of these lines are passing through the corner of any of the numbers. Maybe this one, but even that one looks a bit suspect. So what I'm going to do is extend this line now quite a way until I do go through one of the corners of these, 2 of the corners of these squares. So let's extend it up now from here. So just drawing up and up and up. I'll stop there because that's a nice point for us to take. The other point is here. So that one is accurately going through a corner. So I'm going to draw up from here and then draw along. So I've now got a right-angled triangle with my points very clearly on whole numbers. So I now need to just count up the rise. So this is stage C, so I'm going to write it in here. So the rise is 5, so 5 over the run is 3, 6, 8. So 5/8. And 5/8, if you're not sure about this, in fact, why don't we just do a little calculation to one side? So I'll do it down here because there's not much room. 8 into 5, just using a bus stop method, giving ourselves some extra zeros to work with, and so we've got 0 point, so 8 into 50 goes 6, so 6 8s 48, so carry 2, 8 into 20 is 2, 2 8 16, so carry 4, and now 8 into 45. So we've got 0.625, which you can do on a calculator, or you can use the bus stop method. Okay, meters per second, like that. Now this one is very simple. So stage D, stage D refers to this line here. Stage D, there's no rise at all, so we've got 0 rise. There's a run of 5, so 0 over 5 is 0 meters per second. Nice and easy. Finally, E, where we bring our robot home. Well, let's think of it again in terms of rise over run, but this time I'm going to not rise as much as sink. So I'm going to draw down from here, or in fact let's choose again a line here, so down from here, because that gives us a whole number position, and then we've already got this drawn up to here. So now let's calculate our rise. So again, thinking in terms of rise, well, it's a negative rise, okay? So although I'm going to count these, I'm going to have a negative. So I've got 1, 2, 3, 4, 5, 6, 7, but it's minus 7. So let's write this here, minus 7. And our run is 2, 4, 6, 8, so minus 7 over 8, which is going to give us minus 0.875 meters per second. And that takes our robot home and gives us a complete picture of its journey from its origin, accelerating but calculating by average velocity to here, and then the constant velocity here, which is also the average velocity, constant velocity, 0 velocity, and then an average velocity, negative velocity, because the robot is going in the opposite direction and coming back to the origin. Okay, so finally what I want to do is just think about problems that you might get where we have to rearrange this idea of finding the velocity, and instead of finding the velocity we might be given the velocity, and instead we might have to find either the distance or the time, or the displacement or the change in time, which is what we're basically talking about here. So what we can write here is that the average velocity, so average velocity is equal to the change, and we can notate this with a delta symbol. That's very common, particularly in physics. So the change in distance, well, distance is on the y-axis or the vertical axis here. Instead of y, we'll use s. Okay, so we'll call this the s-axis and this the t-axis, so s and t. So it's the change from, if we look at something like this, at this stage here, it's the rise, in other words, which is the change in the distance values here. So how much up it goes is the change in distance. So we say delta s over the change in time over that period. So delta t. And as we've seen, we get that by subtracting the first distance here, so s1. Looks like this would be 2 in this case, and the second time, so this would be s2, which would be 2, 3, 4, 5, 6, 7, 8. So 8 minus 2 then, so it would be 6. So the rise is 6, but we can express that generally using algebra as s sub 2 minus s sub 1. Now what about the time? Well, that's t sub 1 would be this time value here. That looks like 2, 3, 4, 5, 6, 7. Okay, 7. So t sub 1 is 7, and t sub 2 here, well, that's another 5, so that'd be 12. So 12 minus 7 is going to be 5. So yes, so the run is 5. So we've been counting along, but here now we're using a slightly more mathematical method of subtracting t1 from t2. So t2 minus t1. And what this gives us, in fact, is a formula. And it's very similar to the speed equals distance over time formula, which means we can rearrange it in the same sort of way. So that if we're given a problem like this, so let's have a look at an example exam style problem. So here we've got a particle then, okay? It's moving at 1.2 meters per second between these two time values, t equals 7 and t equals 12. And its starting position is, well, it gives us 3 meters from the origin, so 3 meters from the origin. So we can fill in, so this isn't representative, so let's not just count these, so it's 3 meters from the origin. We're going to use this question though to calculate what our displacement would be, so the distance, in other words, that it would be on the s-axis here, the vertical axis. Okay, so that's the unknown, and so what we might want to do here is just rearrange this formula. Okay, so if we write, instead of average velocity now, I'm just going to write v. So v equals delta s over delta t. Easier at the moment than writing it out longhand like this. So just like the distance time formula, we can rearrange that so that you've got speed, just like this, I should say, the speed, distance, time formula triangle that you might have used up to now. Just in the same way, we can change delta s over delta t. So we multiply both sides by delta t, and we'll have delta s. So if I write therefore delta s equals the velocity times the time. The velocity times the change in time. Okay, like that. Now, if I then go back to this idea of subtracting the first distance from the second distance, then I'll get the displacement. So I've got s2, so I'm just expanding that. S sub 2 minus s sub 1 is what we've got on the left-hand side now. And the velocity we've been given, which is 1.2. And now we're going to multiply by the change in time. Well, that's t2 minus t1. And t2 we were given as 12 minus t1, which is t sub 1, which is 7. Okay, so we've also been given s sub 1, so the first distance here we've been told is 3. So we can now rewrite this s2, which is what we're trying to find, minus 3 equals 1.2 times 12. In fact, why don't I just write times 5 times 5. 12 minus 7 is 5. Okay, so its final position, s sub 2, has got to be, if we add 3 to both sides, 1.2 times 5 plus 3. Okay, and 1.2 times 5 is 1.2 times 10 divided by 2, so that's going to be not 0.6, 6. So 1.2 times 5 is 6, plus our 3 equals 9. So there we go. Simple algebraic rearrangement, and it can be useful if you're given the velocity, in this case, given the average velocity, and you want to find something else, either the time that's elapsed between one point and another, or, in this case, the displacement, the amount that the particle has moved. So its final position, let's just write it out in full. Final position is, whoops, okay, is 9 meters from its origin, or the origin. Okay.